You'll recall when we did derivatives so long ago, we had this little thing called the Fundamental Theorem of Calculus. Well, guess what? There's another one of those. This one pertains to antiderivatives, or we also call them integrals. This one's pretty easy. So we talked about all that conceptual gunk last time, about rectangles shrinking down to 0 or having an infinite number of them and then taking the limit of that sigma squiggly thing to get the function and do all that other garbage. And I said, there's a mechanical way to do this that's a lot easier. And that's what we're going to do today. Okay, and that's actually what the Fundamental Theorem of Calculus is. So we're going to go in reverse order. There's two parts to FTC for integrals. There's a part 2 and a part 1. We're going to do part 2 first, because I think if you do part 2 first, it makes part 1 easier. Then we're going to do part 1, again in reverse order. Okay. Then we're going to talk about the integral as its second concept. So remember, derivatives, there's 3 concepts. We talked about that: rate of change, slope of the tangent line, and instantaneous velocity. For the integrals, we've already talked about the integral being the area under the curve. Today we talk about it as an accumulator. What does the word accumulate mean?
Build up.
Build up, correct, good. And then I'm going to show you another pretty little trick to use on your calculator, which will make your life so much easier. But we'll get to that later. And then today, of course, it's Wednesday, which is always a challenging day of the week. So today, strive to be more positive, right? So I will try to not rip on Push for drawing his integral symbol upside down, because again, I'm going to strive to be more positive and acknowledge the fact that this is America, and he has the right to do it upside down and wrong if he would like. Okay? Here we go. So this is it. This is the little nugget of sweetness that you're looking for with integrals. We want a nice, easy way to be able to find the area under a curve without drawing an infinite number of rectangles, without using some big, scary Greek symbol called a sigma, without taking a limit, because we hated all that gunk too. So we have what's called the second fundamental theorem of calculus. I should say the fundamental theorem of calculus part 2. That's French. And that's a little confusing, but it's actually really simple. So remember when we did derivatives, I'm trying to build an analogy here. When we did derivatives, I started by introducing the difference equation. Remember that f of x plus delta x minus f of x all over delta x? Yeah. And you did that for a while, and you're like, this is dumb. And then I made you take a limit of that, and you're like, this is really dumb. Why are we doing this? And then the next day I taught you the power rule. Right? And it was so much easier. The same thing is true here. So we did the limits. We did the sigma notation. We talked about rectangles. We did all that other gunk, and now I've got this little tidbit of information for you, which will make your life so much easier. So what does this mean? It's really simple. Okay. Oh, by the way, this is really important. Okay? Because it's spun in a circle, so you know it must be important. All you're going to do is take a function, take the antiderivative of it, plug in b. Now remember, b is a number. Plug in a. Again, remember, a is a number. And then subtract the 2 things. Miraculously, that answer you get will be the area under the curve. Okay, so remember, f of x is a function. D of x. Pop quiz here. What's d of x called? What's that thing called? Say it loud, say it proud. The worst that could happen is you're wrong and we just point and make fun of you. Yeah, what's dx called? No, that's a plus c.
Yeah.
Good job, mate. Thanks for the help. You beat me to it. Anybody else? Beautiful. It's okay. It's called the differential. A and B. What are the A and B's called? Nope.
Bounds?
Nope. Well, yeah. Half credit.
Okay.
The domain.
Nope. Limits of integration. Okay.
I was just going to say that, just can't.
Sorry, I was too quick. Remember, A is the smaller number, B is the bigger number. So what is this saying? This is saying what's the area under the curve of that function starting at A and going to B. This little tidbit here will make your life easy because you won't have to draw pictures anymore. You don't care about how many rectangles you got. It's literally just plug and chug. I mean, you got to do an antiderivative still, but you've all mastered that by now, right? Okay, great, let's move on. Let's take something easy. We're moving away from the geometric stuff that you did on Monday, or between Monday and today, where your functions always gave you something like a square, a semicircle, a triangle, a trapezoid, that kind of stuff, and now we're getting a function. You all know what x cubed looks like. It's squiggly. There's no geometric shape that'll fit under an x cubed. And so, how are we going to do it? Well, we're going to use the Fundamental Theorem of Calculus. I'm going to give you 2 minutes to work that bad boy out, or try to work that bad boy out. You might not get it, that's okay, but get in there and get your hands dirty for 2 minutes starting now.
Yeah, 81 divided by
I did.
Yeah, we're writing.
It worked. I changed my motors out to
I was like, at first, like, I wasn't sure if you were writing or not. And so I was like, oh my gosh.
I don't like what I should have done, is I made like a
Yeah, oh, that would have been great. But then I was like, but then as like the video was like, you weren't even 5 hours.
I didn't write this
Yeah, 1 or 2. 2? This was it negative or positive? I just first one.
Same. Well, you're either both right or both wrong. Well, hold on. Let's get a third one here.
Oh, we have a third.
We have 4 opinions now. Third, 4th, 5th, we're on 5. 6, 7, 8, 9, 10, 11, 12, panicking, 12, fraction, 13, put it in a fraction, 14, 15,
I'm just saying, I'd buy a PC.
All right, so we seem to have consensus. 81 over 4, beautiful. So let's talk about, I'm assuming that most, if not all of you got that answer. So let's talk about not necessarily how to do it, because it appears that most of you did it, but how we show this, or how you show work associated with this problem. Okay. All right, so I'm going to take the antiderivative. The antiderivative of x cubed is? Beautiful. Raise the power by 1, multiply by the reciprocal, we get 1/4 x to the 4th. Then I draw a vertical segment. I put the 0 at the bottom, I put the tree on the top. So what does that mean? That means I took the antiderivative of that, I have a function, and now I got to plug and chug. Okay? I don't want to continue to write the squiggly thing because that part of the problem is already completed. Which one do I plug in first? 3. I plugged in the 0, okay, just because it's our first time. You're all fairly bright. You don't need that part of it. 3 to the 4th is 81, right? 9 times 9. So we get 81/4. Any problems? Now you're thinking to yourself, he's tricking us, it's going to get much nastier. And the answer is, no, it's not. If you did okay on the antiderivative portions of this chapter so far, this is not bad. It's just plugging and chugging. Okay. So let's try another one. I mean, you can. It's not wrong. It's like writing x as 1x first. Often people be like, wait. Obviously, they didn't. That's what yeah.
So it's 2x. So one of that.
That's a nice pretty
Okay, here we go.
Well, that was an interesting flip. Like if I give my master students an answer and they get something that's not a pretty answer, like if they got 7 out of 5, they think they did wrong, it's not a pretty answer. Now you're getting a pretty answer and you think it's wrong. Oh, it's not an answer.
Yes.
X to the power of 1. So what's the top one or the bottom?
Yeah.
We're plugging the top one first. Top one's
Writing 2x and 4 to 1, like, it's like some thing.
You're right. Hold on.
I'll announce I'm coming over. Amanda, I am approaching your table. Is that one of those how much caffeine was in it? 4 to the square root of 4. That's more than a Red Bull, a Monster, and a
Oh yeah, well you're gonna have to.
And this is amazing. This is 6. Great is amazing.
Oh.
Is the first step 2? Thank you.
When they do, they die like.
You got 6. You got 14. How you get it? You get it. I just. What do we got? 14. 14 seems to be the consensus. Okay, so working through this couple. There's one new element in here, and that I made the problem a little nastier by putting a fractional exponent in there, but it doesn't matter. You might be saying to yourself, why is the 3 there? I intentionally put the 3 there to make the problem easier. How does the 3 make the problem easier? Hey.
It like gets rid of the third, like in the 3 in the denominator.
Beautiful.
Of 2.
One thing to be careful of when you're starting these problems is making sure that your notation is solid. So notice, all I'm doing is rewriting the problem, so therefore the integral squiggle still needs to be there. The dx still needs to be there. Now I'm going to take the antiderivative. 1/2 plus 1 is 3/2. Multiply by the reciprocal of 3/2, I get 2/3. Okay. So the reason I put the 3 there, as May mentioned, is that will cancel with that and leaves a 2 there. Okay. Good so far? Question? Did I screw up somewhere?
No, do you have to show that step like when you're writing?
No. I'm assuming you could take 2/3 times tree to get 2. Okay, so you could probably skip that step, but again, it's our first day, so I'm doing baby steps before we start sprinting. Pregunta in the front.
There's a small question. Is it
fine if you just write like 1.5 or 3 like halves at
Fractions.
just only fractions?
Okay. Just as a quick review, let's talk about what the fraction 3/2 means. Sorry, that was meant to be a question. What does the fraction 3/2 mean?
1 1/2.
Say that again?
It's like 1 1/2.
Which means what? How do I do it? Everybody's talking at once. Okay, so, all right, hold on. Let's do this. I'm going to assume that you can all do 1 to the 3/2.
Yes.
Okay, good. How would you do without a calculator? How many of you did 4 to the 3/2 with a calculator? Don't be bashful, admit to it. Come on. None of you. Excellent. I mean, it doesn't matter if you did. I don't care. You could have a calculator. How do you do without a calculator? Amanda?
The square root of 4
2.
Oh, okay, yeah, so.
Yeah, I'm with you. And then?
And then you.
Beautiful.
So,
Why did you choose to do the square root first instead of, why didn't you do 4 cubed and then take the square root of that?
I don't know, I think you just.
You don't have to. It's a choice. Like I could do it. 4 cubed is 64. Square root of 64 is 8, which is the same answer you got, right? So why is it smarter to do the square root first? Correct. You're working with smaller numbers, which in general, you know, if that was a 7, for instance, I don't know how many people are going to know 7 cubed off the top of their head or want to calculate it. Whereas taking a square root or a smaller number is easier. Okay, so as she said, square root of 4 is 2, raised to the 3rd power is 8 times 2 is 16, and that's 1. So we should get 14. Okay. Is there anything difficult about this? Good. So there's no tricks here. We're just ramping up a little bit. So if you were me, oh, you know what? You have the slideshows in front of you, don't you? So you know what the next problem is. You don't have the next problem?
No, we
You
do.
do, but.
Yeah, now you do. So I opened my mouth. Sorry. How would you make it more interesting? Put a trig problem in there. All right, go. This, of course, is predicated under the idea that you remember what the antiderivative of c squared is.
I think like monkeys like doing
It's just tangent.
Now, if they win, you're eliminated. They have to start their bonus points. 25 points for the second part, you're performing while you're battling. And then down in the corner, there's 3 questions. How was your routine? How was your routine while you were fighting?
Doing
What? No, you're done. Once you win, your 2 minutes are up. You walk out, you've done your routine, and
Shouldn't the 75?
boxing fight.
Now,
He's gonna fight CT.
Guys, I just.
Oh, I don't
it's cool when he goes on the back.
My personal battle. Nathan, my personal battle is on.
They didn't know it. They made it up as they wanted. But people you want to buy.
Trying to deal with the terms that you know. Stuffing someone.
Winning the battle. So this could be a ongoing thing against Adler's one. Hold on, I gotta finish it. All right, what's the antiderivative of secant squared? Tangent. Beautiful. Okay, so easy peasy. Tangent of x from pi over 4 to 0. Okay. And again, I wasn't lying, KISS method. What's the tangent of pi over 4? 1. What's the tangent of 0? 0. And look, we get a pretty answer of 1.
In this case, do you need to write like tan 1, tan 0, or?
No. It's not a bad idea. Okay, any problems? Okay, easy, yes? Good. So all we're going to do now is we're going to merge what we did in day 4, I think it was 41, with this new extra step of plugging and chugging. So yes, you're going to see some problems where you have to split the fraction. Yes, you're going to see some problems where you have to distribute things. Because remember, there's no product rule, quotient rule, or chain rule in antiderivatives. Okay, beautiful. Let's move on to that guy. I included this one based on the discussion that I had yesterday with Anthony about doing absolute value. Okay, this is not the absolute value of x, so it's not going to be in the shape of a v. What is it going to look like? And we're not going to take the time to work through this whole problem, but May's going to help us out with an answer of, it kind of looks like a W, correct. I got a picture of it, it's right there. Where did that come from? Remember, the absolute value around a function takes anything below the x-axis, flips it up on top. Also notice, I'm only asking you to go from -2 to 3. Well, you'll notice in this picture, -2's over here and 3 stops there. So this is going to require that I split the problem into 2 different parts. One part is going to be this guy over here. The other part is going to be the little parabola-looking thing, the upside-down parabola. Well, how does that matter? It doesn't. You just write 2 different equations. However, you'll notice this and this are different. Why? Anybody other than May?
Because you have to make the equation of the right integral have the shape of the graph.
Good. Okay. So what I did there is I multiplied everything by -1. Why? Because remember what we talked about, or I talked about the other day. If I go from A to B, and let's suppose A is bigger than B, I have to flip it. And if I flip it, I put a minus sign in front of it. Okay. So this is above the x-axis. If I just look at the original parabola, it's below the x-axis. So how do I get it to flip up on top? I put a minus sign in front of it. So there's 2 elements to that problem. One is splitting it into 2 parts. Okay, it splits right here. And the other one is realizing that for the parabola, the curvy part, you have to flip it over because it's above the x-axis. Right. We are never going to talk about how to find the antiderivative of an absolute value without some trick like this. It's just not worth the time and effort. It'll make many of you cry.
So, okay, so we don't need to know how to find where to split it up while we're doing the graph or something?
When you see an absolute value problem, I would rely on a sketch more than anything else. Draw a picture, figure out what you're doing, break it into parts, flip things over, that's it. There isn't going to be some mathematical formula. You're not going to learn some secret about taking the antiderivative of absolute values.
We'll have to graph that then to find.
I wouldn't even say graph it, you just got to sketch it.
Will be on AP test.
Well, how would we?
AP test?
This type of problem?
Well, like, yeah, the absolute value about like.
It could be, not with, do it, no.
Oh,
If it's on the AP test, you're going to do it just like this.
Oh, okay.
Well,
Yeah.
but how do you find that it's negative one that it flips out?
Oh, great question. Why negative 1? How would I find that? How did I find that number?
Because it equals 0.
Right.
So
Yeah, I factored that quadratic and figured out where it equals 0.
Oh, right.
It equals 0 at negative 1 and 3. Good question. Okay. Here's where things get a little weird. The first stuff we did, as it said, is huge. You're going to do it a lot. This is a little bit more niche, so I'm going to go through it pretty quickly. And this gets a little weird. So let me do something different first. Let's suppose I've got and let's go from 7 to x. Okay, this is a little bizarre because we haven't seen this before. I want to take the antiderivative of some function called t squared, and I want to take it from 7 to x. Well, wait, what does that mean? Because we've always put a number in there. Trust me. Okay. So we follow the same procedure we did for the Fundamental Theorem of Calculus on the previous 9 slides. What's the antiderivative of t squared? 1/3 t cubed, and we're going to evaluate from 7 to x. Okay? Any problems there? Good. So now, using that fundamental theorem again, I plug in x first. I get 1/3 x cubed, and I plug in 7. And I get that mess. This would be some big scary number. I don't care what it is because I'll show you why in a second. Any problems so far? Now, I'm going to do one small thing. I'm going to take the derivative of this thing.
Wait, should it be DT?
No.
Like, the variables T.
Yeah. Should be dy dx. Because I'm going to take the derivative of that final answer.
Oh,
What's the derivative of 1/3 x cubed?
T squared.
What's the derivative of this? 0. Okay? The nice thing about this is if you understand what I'm doing, it'll make your life a lot easier. You don't have to do this. Because if you understand what's going on here, I'm taking an antiderivative of some function, I'm plugging in x, and I'm plugging in a number. When I take the derivative of that puppy, that number, regardless of what the starting number is going to disappear. This will always go to 0 because you know that the derivative of a constant is equal to 0. So notice what happens. I went from a number to x, and when I went from a number to x, the number didn't matter because it disappeared, and the only thing that changed is that t's became x's. Okay? So you'll commonly hear me refer to this as a variable change. Now, this is a different way of looking at a function. I'm defining this function g as the derivative, the integral of some other function f. And then I'm going to take the derivative of that. But before I do that, let's talk about something else that's going to become relevant. If I know that g of x is this, just for giggles, what's g prime of x? Say again?
T, like that one variable.
F of x. Okay. So, here, I have a function in terms of t. I can call this something different. I can call it Bill, for instance. If I take the derivative of Bill, all I did is just end up taking the t's and making them x's. Okay? Take the t's and make them x's, and I get back to the original function. What's g double prime of x? F prime of x. And now you start to see a pattern. What's g triple prime? F double prime. Okay, so it's always trailing by 1. When you get into these types of problems and they define a function in terms of another function, these notes will help you. Because then you're going to be asked questions about graphs and all that other stuff, which we'll get to later. Okay? Again, when you see the derivative of an integral going from a number to a variable, you simply replace the variables, which are t's, with x's. Okay? Some of you look completely confused. Are you okay?
Can you repeat that sentence?
Yeah.
Integral with
When you take the derivative of an integral, you simply replace the variables. T's become x's. It doesn't matter what the number is. 0, 7, pi, e. As long as it's a number, you're good to go. Okay, I got one more little tidbit of information about this. What if it's not just x? Okay, what if it's x squared? That's where this comes into play. If it's something other than just x, you have to chain on the derivative of this function up here. Do a variable replacement. So in this case, let me write this out in a different color. Everybody okay back there?
Yeah.
Okay, beautiful. Let's go back here where I got some working room. If I did the derivative of the integral from 7 to x squared of, let's do something, t dt, what would that be? Okay, I'm not going to go through all the work. I'm just going to remember what I need to do. Replace variables with variables. T's become that function. So I get x squared, and I chain on the derivative of that function up there, 2x. If it was t cubed, it would be x squared cubed. Take this puppy, plug it in for all the t's, chain on the derivative of that function. This does not happen very often, but it's part of the fundamental theorem of calculus, so it's something worth talking about. Now here's where they're going to sucker you in with this. They're going to give you a problem that looks like this, and they're going to try to bait you into doing an antiderivative. Okay? So they're going to make you go through all the work that I went through over here, and then you're going to be pissed when you get to the end and you realize it's just x squared. Or they're going to ask you the same question, and they're going to give you a function that you don't know how to take the antiderivative of. Sidebar. When we did derivatives, as far as I can remember, we never ran into a function we couldn't take the derivative of.
Mm-hmm. Well, things with where you had to do L'Hopital's rule, and like if it never.
But those were limits.
That was limits. Yeah.
Right.
No.
There are lots and lots and lots of functions that you won't know how to do the antiderivative of, or the integral of. Okay, so this isn't always as pretty as the derivatives.
What types of functions?
Absolute value.
Okay. Right.
Some weird trig functions,
Yeah.
like a tangent squared. All kinds of. We'll get to some.
Okay.
Yeah. Okay, so here's how it's illustrated again. I already did this, but again, taking the derivative with x squared. T's become x squareds, chain on the derivative of x squared. Okay? Don't freak out about this. It's okay. Fundamental Theorem of Calculus Part 1 is not that interesting. Okay, let's take a break with something easier. Bust out your calculators. You're going to like this. Now, depending on how new or old your calculator is, you may have to handle this differently. So to start, hit Math 9. And tell me what shows up. Do you all get the squiggly symbol?
Yeah.
Does anybody not get the squiggly symbol? Life is grand. Then it's so much easier because it's ridiculously obvious what to do. So let's do an example. Let's use one of the ones we did before, and that was, let's see, in a lovely shade of yellow, we had the antiderivative of, what did we do? X squared dx from what to what? What was the previous example?
I don't get it. I don't
Oh, okay, I'll come back to you in a second. Was it?
It was 7x squared t is 2.
No, hold on, I'll find it. That guy, 0 to 3, thank you. So we know, hold on, we know the answer should be 81/4. Okay, so. Whoa, slow down. 0 to 3. For those of you that got the squiggly symbol, I think you understand what you're supposed to do. Do it. Put in x squared into one of the boxes. Put 0 in another box. Put 3 in the other box. Put x in the far right box. Is that great?
X cubed.
That's what I meant. It was x cubed, sorry. Okay, Leona, I'm sorry, but you're going to have to write this bad boy down. For you, you're going to type this in. When this will pop up automatically, and you're going to do parentheses, the function, comma x, that's always going to be x, comma 0, comma 3, close parentheses. It's a pain in the butt. I'm sorry. Please tell me you got 81/4.
Yeah.
Okay, this is commonly referred to as fn int. It will tell you the area under any curve through any interval. It'll do any problem, for the most part. But all it will do is give you a numerical value. However, that's a good thing. Each one of these problems that we did earlier can be solved, solved using that fn int. Like I talked about with the programs that I gave you, the RSum and RSums program, use the technology at hand. When you're on the calculus portion of the AP test, you will always fn int everything. You'll never do that on a calculator portion of the AP test. However, sometimes in here, I will make you show me the antiderivative. Okay? In other words, if I gave you this as a problem, you might have it on a calculator test, but the problem might say show your antiderivative. That's because I'm going to give you a calculator for other problems, but for this one, I'm going to want to see that step. On the AP test, nobody cares. They know you have a calculator. They know your teacher should have shown you how to fn int. They're expecting you to fn int all of those problems. Okay? Question?
So the quiz on Friday, I wouldn't be able to like FNN. I know, but like.
I don't think this is on the quiz on Friday.
Then like for the other things.
It depends on the problem.
Got it.
Okay, last thing and then we're done. I have this graph. I called it F of t. And now I want to introduce the idea of an accumulator. And as we mentioned already, an accumulator adds things up. So think about starting at 0 and moving to the right. As I move to the right, the area under the curve gets bigger and bigger. Until when?
Until 3.
Until 3. And then what happens?
It's getting lower.
It's getting smaller. What you want to think about is that it's getting smaller because I'm adding negative area. It seems like semantics, but it'll help you process this a little bit easier. and think about the area like lining up a bunch of pencils. Okay, so I take a little pencil, and I start adding up pencils. So pencil here, pencil here, and then I got all these pencils, and eventually you get the big 64 box with the sharpener on the back. As I move to the right, I continue adding area, and I'm accumulating that area as I move to the right. Okay? Now, one of the last things we'll do is we'll talk about what happens when you go to the left, but that comes later. So number, to the left. It'll be fun, you'll love it. What's g of 0? Why?
Because there's no area depth at all.
This thing up here in red tells me I'm starting at 0, and I'm adding up the area from 0 to some number. Well, what is that number? That number is determined by this. Okay? What's g of 1?
2.
Why?
Because it's like 2 on 1.
Nope.
Because it's a triangle, so you do 2 times 1.
So what should it be?
1.
1. Is everybody okay with why that's 1? What I'm asking you for then is, what's the area of that triangle? 1. Okay? Done. Let me change colors here. Purple. What's g of 2? How much?
3.
Why?
Because you're adding 2, which is the rectangle, to plus 1, which is the triangle.
Okay. Any problems? Beautiful. What's the approximate value of g of 3? Nope.
Or 4.
A little bit more than 4. Yeah. So if you look at boxes now, I've got 3 up to here. I'm adding almost a full box, and then maybe half of a box.
Like 4.5?
Yeah, somewhere around 4.5. I'd guess about 4.5. What about g of 4? Will it be bigger or smaller than 4.5?
Smaller.
Good, because we start to subtract area now.
Probably over
It would actually be, it would be exactly 3.
Will it?
Well, it will because I did the graph and I know that it's symmetric. So
Okay, yeah.
I know that this area is equal to that area. So yes, it would be 3.
Can you like assume that on
It's a problem asked approximate, so
okay.
they're not going to penalize you unless you write a long dissertation on the exam. Let's get to the fun question. Number 7. Where does g have a maximum value? Good. Why?
Because after that section small.
Good. I'm adding area from 0 going forward. I continue to add area, little slivers of pencils, until I get to 3. And then at 3, I start to add negative numbers. Okay, and again, notice how I'm phrasing it. I'm adding negative area. I'm not subtracting area. Where's it a minimum? 0? Why?
Because if you added, if you said 5, then like it would still be a little bit higher than 7.
Let me rephrase my question then first. Where are possible candidates for a minimum?
5 and 0.
5 and 0. Okay, is everybody good with that statement? 0 is obviously a candidate because the area is 0. 5 would be a candidate because of why?
Subtracted the most.
Finish your sentence.
You subtracted the most area throughout the.
Let me change your vocabulary a bit.
Yeah.
You added the most amount of negative area.
Yeah. Yes.
Okay. So, if 0 and 5 are my candidates, we need to discuss which is which. I know that g of 0 is 0. The question is, do you think that this negative area is bigger than the purple positive area? If the answer is yes, then all of a sudden 5 becomes the minimum. If the answer is no, then 0 becomes the minimum. If, however, you think that the red and the purple are the same area, then we've got a problem. Because we have 2 minimums, then they would both be 0. I would argue that the purple has a bigger area than the red, so therefore the minimum would be at 0.
So what would you do if they were equal? What would you write?
Quit. Give up, cry. Right.
So they probably won't ask that.
Or you could say 0, comma 5, right?
Any questions about this? Okay, let's change the problem then. Let me get rid of this mess. I want to redefine G. I'm going to make G equal to this equal to 3. Okay. And we're just going to do one of these. We're not going to go through all these. I'm just going to ask you this. Actually, I lied. Let's make it easier. Let's make this 2. Okay? So if I redefine G as going from 2 to some number, what is G of 1? Invalid? Is that what you said, or did you say valid question?
Oh, actually, no.
What'd you call me, Ashley? Mr. Ashley to you, buddy.
No, never mind. You could do that actually, because it would
You
be
can.
the bounds would be
There's an
from-
answer.
from x to 2. I mean from
Yeah.
2 to 1.
So what's the answer, though?
Negative 1. Negative 2, I mean. It would be negative 2.
Negative 2?
Yes.
It's above the x-axis.
But you're going backwards.
Wait.
I think it changes the thing. I'm pretty sure.
Many of you look confused, so I'll clarify. Okay. What does this mean? It means, get rid of that, put this back in here. This is saying what is the area under the curve from 2 to 1 of f of t dt. And notice my top limit of integration is bigger than my bottom limit of integration. We have a way to fix that. What's the way to fix it? You flip it over. If you flip it over, however, you've got to put a minus sign in front of it. This, from 1 to 2, is 2. Okay? 1 block here, 1 block there. But we have a minus sign in front of it, so it becomes negative 2. Good.
Wait, but weren't the bounds 2 that? Oh, wait, no. Yeah, we tried to.
So initially I started, not initially, but last time I said, well, if it's below the x-axis, it has to be a negative area. But now we complicated things by saying you can also get a negative area if you go backwards. And I think last class somebody mentioned vectors. Okay, so if I go that direction, it's positive. If I go the opposite direction, it's the same speed, but it's negative, so it becomes a velocity. The same concept is here. If I go from left to right, then above is positive, below is negative. If I go from right to left, below is positive, above is negative. Okay? We good? When the problems get complicated, if you remember that title, the integral is an accumulator, and that you're adding areas, it will make your life a lot easier. That's a breakdown of all the stuff we already talked about, just pictures of showing that. Do you have a question?
I just wanted, I'm pretty sure it's true, but it's like if you have the definite integral and it goes from 1 to 2, you subtract that. I mean, yeah, of course, because it's like negative, so yeah, never mind. Okay.
Glad I could help. What's the difference between displacement and total distance? Now we heard enough out of you. Are you raising your hand?
Assuming displacement is like
find the positive and negative values.
If I'm gonna cha-cha, you know how to cha-cha?
Like the cha-cha recipe.
Sure. You do the cha-cha, you know, when you cha-cha, you do this, and then, you know, so if I cha-cha here, and I cha-cha here, and then I cha-cha here, and then cha-cha here, what's my displacement? 0. What's my total distance? Approximate. I cha-cha'd 4 times, by the way. 8, good. Figuring I step forward 2 feet, back 2 feet, so maybe 8, 16, whatever, it doesn't matter. Displacement is the difference between where you start and where you end. Total distance is the total distance covered. If you leave your house and go to grandma's, turn around and come home, your displacement is 0. What's your total distance? How's far grandma live? 2 miles. So your total distance is 4. Okay? So the concept is okay. From a mathematical standpoint, we have those 2 things. We talked already about the antiderivative. The antiderivative of velocity is position. If you do it without absolute value bars, you're going to get your displacement. If you put the absolute value in there, you'll get the total distance. It takes negative velocity, and the absolute value makes it positive, and so you're taking 2 plus negative 2 to make it 2, 2 plus negative 2, this negative, and you get the total number. Without the absolute value bar, it takes 2 plus negative 2, 2 plus negative 2, 2 plus negative 2, and gets us back to 0. This, right one, you're always going to fn into. The left one, however, you may have to grind out, depending on the function that they give you. So, just to practice fn int, do that. By the way, this will be a fun little, I'm going to mention the P word here. For those of you that are good at physics, what would that equation describe from a physics standpoint?
Position?
Describe a situation where that function would come into play. Ball. What about the ball? Falling from a height of 100, and it's just dropped? No. What have I done with that ball from 100 feet in the air? 100 meters in the air. Sorry, it would be meters. I think it's meters. No, that's feet, right? Negative 32 feet, or feet per second.
Oh.
That's, yeah, so we're in feet here. So I'm 100 feet up, I got a ball. Am I just dropping the ball, Lauren? What am I doing with it? Throwing it up, down, out, at myself? Hold on. I'm not going up with the ball. I'm throwing it down with a lot of anger. Right, 42 feet per second downward. So that'd be like a t-shirt cannon or something. Irrelevant to the problem.
What if it was like a coin, you hit someone on the
And they die.
It's like you're not trying to figure out if it's dangerous to drop it, you're like actively trying to make it dangerous. Throwing it down off the A coin probably won't hurt.
Okay, so you get the idea here? You can, wait, let me finish. You can do the antiderivative of that function, it's not too bad. Okay, negative 16 thirds t cubed minus 21t squared plus 100t. You could plug in 0, plug in 10, or plug in 10, plug in 0, subtract, get your answer. The absolute value bar, you don't know how to do that, so you would rely on fn int to plug that in. You should know how to plug it into fn int. Again, fn int is not rocket science. It pretty much tells you what to do. It gives you this picture. You just got to plug a jug. Okay? And you get your answer. Those answers should be different, I think. Let's pretend they are. Okay? Good. We're all done. You know what's better?
Oh, I just need help with, do that.
Excellent. I'll be there in 1 second. Let me wrap this bad boy up, and then we'll be good to go. Discard.